This week, we are going to talk about mathematical proofs, axiomatic systems, methods of proof, and especially mathematical induction as a method of proof. And finally, we'll talk about recursive definitions and, of course, its relation to mathematical induction. To start with, what's a mathematical proof? A mathematical proof is an argument for a mathematical statement or a proposition showing that the stated premises logically entail the conclusion via accepted rules of inference. So we have talked about inference rules in the last lecture, be it in the propositional logic or in first order logic, or indeed in higher order logics, which we didn't talk about. But generally speaking, a mathematical proof is showing that an argument is valid. Essentially, that's it. But of course, you have to be careful about setting up the premises and expressing the conclusion in relation to those premises. These premises are going to be either definitions or axioms or theorems, which can be established before. So the premises can consist of all these types, and among these, the axioms are certain assumptions, essentially that we accept to be true, and they lay out the landscape of the system where the proof holds. Essentially, axioms describe what kind of universe your proposition or your theorem lives in. And theorems here are previously proven statements. So any theorem that you have the proof to, which is now established as a truth, you can use in your proofs. Okay, so essentially this is what a mathematical proof is in a general sense. And the next question we should talk about is, why do we need them? Why do we do mathematical proofs? First of all, they provide truths about certain relationships in certain settings under certain conditions. So we know in a more general sense, in the most general sense possible, that a given proposition is true, let's say. And the proofs also provide insight to certain situations, certain relationships, certain identities that we can make use of in similar circumstances, or we can apply to other scenarios, let's say, or we can use them to prove other theorems that provide useful. And finally, they provide guidelines and borders for what we can and cannot do using mathematical tools in a practical sense. So from an engineering point of view, for instance, if you are doing something that involves computation, for instance, you might need to derive bounds for numerical errors. And for these, maybe you can prove certain bounds on your errors, or maybe you can prove some convergence properties, maybe convergence rates, or maybe you can, in the context of computational complexity, which we'll talk about later on in this course, for instance, you can prove that a problem is so difficult that it is reasonable to use an approximate solution rather than an exact one, for instance. You can actually mathematically show that certain problems are so difficult that it's practically not a smart thing to do to look for exact solutions. So in such cases, for instance, you are entitled to go after approximate ones. So mathematical proofs in general provide us with this information. Okay, so proofs in a general sense live in axiomatic systems. So they are based on certain axioms And an axiom, as we have talked about, is an elementary assumption. Okay, so you use them to define what sort of universe you are building your mathematics in, and what kind of setting you are proving your theorem, let's say, in, so that they limit you, or they define the settings that your proof is going to work. So in a general sense, we can define an axiomatic system as any set of axioms from which some or all axioms can be used in conjunction to logically derive theorems. Okay, so an axiomatic system essentially is a collection of axioms. Okay, and they, of course, they have to have certain properties to be useful. We say that an axiomatic system is consistent, okay, consistent, if it lacks contradiction. Okay, so you have a number of axioms, and if there's a contradiction between any two, then, well, remember that based on a false premise, you can show the truth of any proposition, because false implies anything. Okay, therefore, if you have a contradiction in your set of axioms, that's a problem, because then your set of axioms is not really useful, because essentially you can prove anything. So you look for consistency. Okay, so consistency is essential for an axiomatic system to be actually meaningful or useful. A second property is called independence. In an axiomatic system, an axiom, one of the axioms, let's say, is called independent if it's not a theorem. Or in other words, it's independent from the other axioms if you cannot derive it from the others. Okay? Independency by itself is not essential like consistency, but as you very well know, in general, we would like to minimize the number of axioms we use in our axiomatic system. And finally, we say that an axiomatic system is complete if every statement can be proven or disproven. Okay, every statement, of course, in that universe, let's say, involving all definitions, all relationships that can be thought of. If you can prove them all or disprove, that means you are able to assign a truth value, either true or false. That means you actually can talk about the truth value of any given proposition in your axiomatic system. Then we say that system is complete. Okay, so the choice of axioms is essential in any mathematical system. And if you start with a different set of axioms, for instance, you basically define new mathematics. As long as they are consistent, it gives you new conclusions. So based on your axioms, you can build mathematical systems, you can define operations, you can prove theorems, etc. Essentially, you define new mathematics.